Okay, so here's the final, well, at least depending on which, I guess, series I put it in. For second semester, I usually stop here. Nuclear chemistry. So this is a general idea of nuclear chemistry that the nucleus actually has conflicting forces. There's a nuclear strong force holding it together, but there's the electrostatic force trying to rip it apart. So if you remember the four fundamental forces, there's gravity, electrostatic, nuclear weak, nuclear strong, and maybe you could call dark energy one of the forces. Uh, so the electrostatic force, you have the positive nuclei or positive protons trying to repel, but then they have this stronger force called the nuclear strong force that holds them together. And the nuclear weak, that's the force that binds quarks together to form protons and neutrons. Neutrons can also exhibit the nuclear strong force, and they act kind of like glue that stick the nucleus together. And but then there's this balance between the nuclear strong force and the electrostatic force that's trying to rip the nucleus apart. And if the nucleus is no longer stable, we have a special word for that. We call it radioactive. Originally, they could find radio waves coming from it, but there's much more than radio waves, much more dangerous radiation coming from radioactive nuclei, unstable nuclei. We'll talk about that in a little bit soon. And so I'll let you know another hint. I was studying to be a nuclear physicist, and I can tell you nuclear physics is so much easier than chemistry. So electrons, they're really close in energy levels, and they interfere with each other, and the calculations for electrons are so difficult. Protons and neutrons, they have energy levels, they have wave functions, they have like p orbitals, s orbitals, all those things. The difference is the energy levels are so far apart and they don't interfere with each other. It makes the math so much easier. So electrons, the same. You understand electrons, you understand protons, but the difference is that the energy levels are so large. But the same rules when you have excitation and relaxation, just like with electrons, except for protons and neutrons. When they excite and relax, they give off gamma radiation instead of visible light, typically. So this should be a review, hopefully. That the top number is a mass number. It's the number of protons plus the number of neutrons. Bottom number is the atomic number, sometimes referred to as Z. It's the number. It's the number of protons. And balancing nuclear equations is really easy. You just have the top numbers and the bottom numbers have to be the same. And I'll show you some of these, and then we'll do a couple examples. Oh, and the types of radiation: alpha, beta, gamma. Alpha, it's the lowercase alpha particles. Alpha particles is a helium nucleus. Beta particle is an electron, and a gamma particle is a high energy photon. So let's look here. So there's alpha particle, alpha decay. So like uranium 238, this alpha decays. The original nucleotide is called, or nucleide is called the parent. So the original one is a parent, and anything that's formed are daughters. So it's very it's matriarchal in nuclear science. So every single creation has a daughter. And a helium nucleus, this is an alpha particle. It's a helium-4 nucleus. And whenever there is a type of radioactive decay, gamma particle ray, are always produced. So even if there is a alpha decay, it's going to correspond with a gamma ray. So it's real easy to find radiation. Radiation is very easy to find. I found 9 grams of thorium that were in sealed glass jars in the back of a cabinet through a wooden cabinet. So it's in thorium goes through alpha decay as well. It's the gamma that you detect. It's real easy to find radiation. So and that was a nice thing about working in a radioactive lab, is that you scanned your body at the end of the day and they couldn't find any radiation. You know you were fine. You were not contaminated at all. So, but okay, so alpha decay there. So any decay is going to have a gamma ray coming off. Alpha particles are really easy to block. You can block it with your skin or a sheet of paper. So alphas are the easiest to block. Now the problem with alphas is you don't want them in your body. So an alpha emitter is something you do not want in your body because it will zigzag around. It'll be like a pinball. If you ever seen an old pinball game, that's what an alpha particle. It beep 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 beep. It just rips apart your insides and cause lots of damage. So you do not want to inhale or consume an alpha emitter. But an alpha emitter outside your body is fine. Beta decay. So this is a beta decay. A neutron actually will break apart into a proton and electron on its own. And neutrons, because those neutrons are slightly more massive than protons, and the electron produced is a beta particle. So notice some of these things. So on the top equations, so right up here, notice that the 92 equals 90 plus 2 plus 0. So the top numbers are the same. And 238 is, in fact, 234 plus 4 plus 0. So the bottom numbers and the top numbers are the same. So same thing with a neutron here. 1 equals 1 plus 0, and 0 also equals 1 minus 1. So the top numbers and the bottom numbers are the same for nuclear equations. Beta particles, one thing with alpha decay decreases the atomic number by 2. Beta decay increases the atomic number by 1. So remember, an element is defined by the number of protons. So these how you can get different elements being formed. Beta you can block with like a block of beta can be stopped by a block of wood or like a thin sheet of metal, something like aluminum, like a frying pan would block a beta particle. So it's pretty easy to block those. Your eyes are pretty sensitive to beta particles. If you work around them, you can get cataracts from the beta particles coming to your eyes. So it's important to wear like safety glasses if you do work around radiation. And plastic is a pretty good beta absorber. It's really hard to absorb gamma. You need like feet of lead or meters of concrete. So on the order of 3 meters, so 10 feet of concrete will stop most gamma rays, and a foot or 2 of lead will stop most gamma rays. So they're pretty hard to stop. And and the other thing with beta decay, if you have a beta emitter, the thing that you want to avoid around it is metal. I just said that you can have like a block of metal. So just make sure the metal is sufficiently thick enough, because beta particles hitting metal produce X-rays. So and if you produce X-rays, then that can cause damage too. So just be careful with that. Positron emission. So this is antimatter. So what is antimatter? Antimatter is matter. It's just like matter. Matter and antimatter are very similar, except the charges are opposite and the handedness of the spin is opposite. So we have matter obey the right-handed rule for electron spins, and for any type of fermion, matter fermion has the right-hand rule. The antimatter fermions are going to have the left-handed rule, and that's more of a calculus concept if you go and study more advanced calculus. When matter meets antimatter, they annihilate each other and turn into energy. So a positron is an antimatter electron, anti-electron. It meets an electron and it generates gamma rays. So it turns into energy. So positron emission, this is important later. We'll talk about PET scans, the positron emission topography. You can use it to map your brain. Also, electron capture is another one. So this way, a positron emission, a proton can turn into a neutron and a positron. And electron capture, a proton will absorb an electron and become a neutron. So sometimes this is called K capture for Kern for first. So that was, I believe, a German word. So if you see K capture, it means electron capture. But English has been ruling science since the end of World War II. So you don't typically see German stuff as much anymore. And so here's summarizes the different types of radioactive decay. So alpha ray, I keep on saying ray. You can use particle and ray interchangeably for these. There's something called the de Broglie wavelength, so you can call them rays because they do have wave-like properties, and the photons also have particle-like properties. So that's one bad habit that nuclear phys. I'm not a nuclear physicist anymore, at least. That's a bad habit that nuclear physicists have, as they refer to particles and matter interchangeably as waves and particles. And the other thing is that sometimes we give masses in terms of energy. So, like an electron has a mass, you could say it's uh, so it's 3.1 times 10 to the minus 29 kilograms. I think it's 3.1. I believe that's the mass of a electron, and then it can also be has the energy equivalent of 0.5 mega electron volts. An electron volt is 10 to the minus 19 joules. 1.6 times 10 to the minus 19 joules. Anyways, so let's go back to this. An alpha part as alpha decay, and you can see that what happens to the mass decreases by 4. The charge decreases by 2. Beta decay, the charge stays, the mass stays the same. The protons increase by 1. Gamma, gamma emission, and whenever you have any of these things are going to have a gamma emission. Positron emission, so you have there's no change in the mass, but the number of protons decreased by 1. Same thing with electron capture, so it's very similar for that. And if you're wondering how can you tell the difference between positron emission and neutron or electron capture, it has to do with the radiation coming off, because the positron meets the electron and gives off that characteristic photon from that, if you're wondering. Okay, and here are all the nucleotides. So you can see here on the y-axis you have the number of neutrons, and the x-axis the number of protons. And in the yellow is is what we have, the quasi-stable nucleides, and then the stable ones are written there in the kind of the blue dots there. And you can see that originally you have the number of protons equals the number of neutrons the same, but then the graph goes up. We have more neutrons than protons, and that's because as the nucleus becomes more massive, there's much more of a positive charge, so there needs to be more neutrons to act like glue to carry that nuclear strong force but have no charge, but keep all those positive protons all together. And so if you remember with chemistry, we have so the magic numbers. Those are the noble gas configurations. The electrons are in that number are very stable. There's these magic numbers for nuclear chemistry as well: 2, 8, 20, 28, 50, 82, and 126. Of these, the most magic number is 28. So 28 is extremely stable for protons and neutrons. Also, the other thing, having even numbers is very stable as well. There's only very few odd number of neutrons, odd number of protons, nuclei that are stable. Most of them have an even number of neutrons in them, so there's very few. And the other thing is that when you have an odd number of neutrons and then you add one, that releases something called the pairing energy. And that can cause things like nuclear fission and various other things. So, okay, so here's an example here, although I didn't even bother cutting it off because it's easy. It's better just to see it written. Write the nuclear expression for each type of decay. Beta decay for berkelium 249. So it holds close to my heart because I went to Berkeley. That's where I got my PhD. So berkelium has a beta decay. It loses a beta particle, which is an electron. And you have this, so lose an electron, so electron is -1. That means that the element's going to go up by 1 atomic number. And then the mass number doesn't change. So, and you just have to look up element number 98 on the periodic table, and it's californium. I guess you never would guess where berkelium and californium were discovered. So there's californium there. And okay, so notice the top numbers equal the bottom number. Positron emission of oxygen 15. So positron here is the particle, So it has a +1. That means that the atomic number is going to go down by 1. There's no change in mass, so it's still 15, and the atomic number for 7 is nitrogen. So right there, there is nitrogen there. And then electron capture in iodine 111. So electron capture, adding the electron there, and that means that the bottom numbers need to be the same, or have to be equivalent, so it's 52. There's no change in mass. Top number is 111, and then it's tellurium. So 111 tellurium. Okay, so I mentioned radiation. How do you detect it? One of them is using a film badge. So these are also referred to as dosimeters. So if you ever work around somewhere there's radiation, if you're an X-ray technician, if you work in a nuclear power plant, if you work in a radioactive lab, you have a film badge, and this is to monitor a person's dose. So it's a long-term exposure. And then after so much time, like a couple months or so, they take your dosimeter and they see what your dose is, and that's just to see like how you're doing, like how much you can get. So we'll talk about radiation later. The average person is allowed for at least from the United States, we consider the average person allowed to receive 5 rem of radiation. I've never received anywhere close to that. The closest I ever got exposed to was 400 millirem. That's when I got a CT scan. But so also, if you get trained, which is not that difficult, you're allowed to receive 10 rem. The workers in the Fukushima power plant, they receive 25 rem, which is not that bad. It's not enough to give you radiation sickness, but we'll talk about that later. So the film badge, that's one. That's to the people. For older people, sometimes they call them radiation shields. I believe that's from the Dr. No, the James Bond film. They called them radiation shields, but they really don't shield you at all. They just measure your dose. So Geiger-Moller counter. So Geiger counter is usually what they call it. This is a Geiger counter. You have argon gas, and then if the particle goes through, it knocks off electrons, and then the detector detects the electrons. And that's really easy. It's a clicking one that click 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 click. You can also have a scintillation counter. These are usually tied to another like a lights, like a photomultiplier tube, so we can measure the light. So cesium iodide or sodium iodide or something like that. When radiation goes through it, it makes a flash, and the flash is the ultraviolet light, and you can detect the ultraviolet light. So you can use these for long-term studies and like tie it into a computer for that. Yeah, you typically won't have a scintillation counter that you carried around. Those are usually Geiger counters. And like I said before, well, what about alpha particles? What are the things like you can detect? Well, whenever there's an alpha decay, there's going to be a photon coming off a gamma ray. So whenever there's a change there. Okay, so let's talk about some radioactive decay, and I wanted to remind you a few things. So if you remember from the kinetics chapter, the first order in nuclear decay follows first order kinetics, and this is the first order integrated rate law. The natural log of concentration at some time is equal to minus kT, k being the rate constant, plus the natural log of the initial concentration, or you can write this as natural log of the concentration at some time over the initial is equal to minus the rate constant times time. Also, we talked about half-lives. Half-lives, it's the natural log of 2 divided by k. So that's the half-life expression for the first order kinetics. And the half-life for carbon 14 is 5715 years. So here's a problem. A skull believed to belong to an ancient human being has a carbon-14 decay rate of 4.5 disintegrations per minute of carbon. If living organisms have a decay rate of 15.3 disintegrations per minute, how old is the skull? Okay, so this is your AT and this is your A0. So, and the idea behind carbon dating is that the average amount of radioactive carbon-14 in living things is about constant. So carbon-14 is formed by radiation from the sun hitting the atmosphere, forms radioactive carbon dioxide. Radioactive carbon dioxide is then incorporated into plants. Uh, other creatures eat plants. Other creatures eat creatures that eat plants. And the carbon-14 will decay, but as you are living, you are still eating plants, eating other animals, or you're a plant, you photosynthesize, or if you're a fungi, you decay those that have been eating, and the amount of carbon-14 stays relatively constant until you die. And if you die, that means you're no longer eating, you're no longer uh, eating those plants and other animals. And for a human that dies, then the human just sits and waits, and then the carbon-14 decays, but it's not replaced because you're not consuming. So that's the idea behind carbon-14 dating. It's not going to work as much anymore for us because of radiation. So we mostly our nuclear weapons program. We blew up 500 nuclear weapons in the atmosphere in between the 1940s and the 1960s. So we blew up a bunch of nuclear weapons. We stopped blowing up nuclear weapons about in George Bush #1. I guess that was around 1990. Was that we signed a treaty that we would stop blowing up nuclear weapons. We would blow them up just around, like in Nevada. We did blow up a lot of them in Nevada. We blew them up underground, though. There's been a few nuclear detonations since then with North Korea, and although they had really kind of crappy bombs, they're not very effective. But India, Pakistan, they have some effective nuclear weapons. But either way, these, especially those previous atmospheric detonations, have changed the amount of carbon-14 that's in the atmosphere. It's skewed it on the high end. So we are a little bit more radioactive because of that, because of the nuclear weapons program. Okay, but this one should be fine. So let me write out the equation. So we're going to use, I'll change this to blue. We're going to use this equation. It's going to be natural log of 4.5 all over 15.3 equals minus kt. So we're going to divide by, we're going to put a minus there and divide by k to get the time. And k, what is k? K is a natural log of, well, t1/2 is ln 2 over k, which implies k is the natural log of 2 over the half-life. So we're going to plug this into here, and just so then the natural log of 2 over the half-life, which is 5715 years. That's a 5. 5 years. And then you put that all in your calculator, and you get, where is that? And you get 100,000 years. 1.0 times 10. Actually, that's 10,000 years. 1.0 times 10 to the 4. So 10,000 years old. So that's how they do radioactive carbon dating. So it's pretty easy to do. It's just as far as measuring the radiation and just making sure you don't contaminate your sample. But it's not that difficult to do carbon-14 dating. Very easy. I've never done it myself, but the math is so easy. So, okay, what about other applications of nuclear chemistry? One of them is nuclear power. Well, nuclear weapons and nuclear power. So nuclear power, though, is the preferred. It's the safer route, of course. So this shows the nuclear chain reaction. And you have a neutron. So, we didn't cover this. You can get spontaneous fission. So there's some elements that they just break apart spontaneously. That's called spontaneous fission. It's a round of decay. And so uranium does a little bit. Plutonium has a much higher rate of spontaneous decay. californium has a huge source of spontaneous decay. Californium is a great source of neutrons for that as well. So, but every once in a while, a random uranium atom will spontaneously fizz, and it'll release neutrons, and then those neutrons can go and be absorbed. If they're absorbed by the uranium-235, that odd number, it pairs up the neutrons and it creates like an excited nucleus, and then the excited nucleus breaks apart. That's also something called the liquid drop model. So uh, and but then the neutron pairs up and releases the pairing energy and excites the nucleus, and the nucleus is excited and can then it breaks apart, and that's called nuclear fission. So breaks apart, and then it generates neutrons. Some in the byproducts, there's a various range of byproducts that comes off of it, but they generate typically 2 or 3 neutrons. It's not as evenly split as this one is showing. It doesn't only produce one product; it produces a range of products. And but then these neutrons can go and be absorbed by other nuclei, and then you can get what's called a nuclear chain reaction, and it sustains itself, and then it generates heat. And we can do that for a nuclear reactor. So here's an example of a nuclear reactor. This is known as a pressurized water reactor. So there's a bunch of different types of nuclear reactors. This is just one. And you have the nuclear core here, and in the core, it's where the nuclear fission takes place, and then it generates heat. Well, it generates gamma rays, and then that gets absorbed by a medium, and then it's usually water is what we put in these plants, and that generates heat, and then that heat is then brought over to a heat exchanger and generates steam, which turns a turbine. And we talked about how electricity was formed in the thermodynamics lecture. You have a couple different ways. You can have what's called a boiling water reactor, where the nuclear reactor is right here, and then that's what generates steam. So that's called a boiling water reactor. You can have, instead of water, we typically do in the United States, is we have water as the medium in here. You can use heavy water. So water, just light water, has protons. The heavy water has deuterium, so heavy hydrogen instead of light hydrogen, also called protium. No one calls it protium except for weird eccentric chemistry people like myself. So that's another way you can make a nuclear power plant. You can also use liquid sodium. So liquid sodium is another way you could do it. You can use graphite. That's what they did in Chernobyl, and that didn't work out too well, of course, because among other things, graphite is flammable. Well, so is liquid sodium. Liquid sodium, that plant almost cannot melt down. The liquid sodium is a great way to go. Just as long as you don't puncture it, then that's really bad news bears. But liquid sodium power plant's it's one that will never melt down really. They also use those as breeder reactors. You can use that to make it's effective to make breeder reactors to make plutonium. Because as you run these, you transmutate. We'll talk about transmutation later. You make plutonium, and if the plutonium is a nuclear fuel. It can also be used as a nuclear weapon. So generally speaking, I won't talk too much about nuclear weapons. It's not really in the book. If you want to know more, you can ask me and come to my office hours. I'll tell you all that I know about nuclear weapons. But generally speaking, a nuclear weapon has an uncontrolled nuclear chain reaction, where a nuclear power plant has a controlled nuclear chain reaction. And how do we control it? Among other things, we have control rods. Control rods absorb neutrons, and you absorb the neutrons, you stop the nuclear chain reaction. And one thing though, that the core of it is, it's hot. It's literally hot, but it's also hot. Also means radioactive. The leftover materials are very radioactive, and as they decay down, they form heat. So they have to be constantly cooled. Otherwise, they can melt. And among other things, that's one of the things that happened in Fukushima. The reactor shut off, but the reactor core still caused the meltdown. Okay, so let's talk about nuclear binding energy here. So the y-axis on this chart is the binding energy per nucleon, and the x-axis is the mass number. And it turns out the most stable of any nucleus is the iron 56. Well, 56. That is the most stable of all the nuclei. So, and uh, this is particularly important for stars and star life cycles. So you notice here there's a spike here for helium, and there's also higher than that carbon-12. So our sun, the stars, they get their energy by nuclear fusion. And if you notice here before iron 56, if you have nuclear fusion, it's exothermic. It generates energy. And after iron 56, nuclear fission is exothermic. That's the so breaking apart uranium into different parts is exothermic. But if you see here, here's hydrogen forming helium. Look at the size of this line here. So the fusion from hydrogen to helium, and even this is heavy hydrogen too. This is, I mean, it's even be bigger for protium. So light hydrogen, that's much more exothermic. So fusion is many times more exothermic than nuclear fission for the heavy elements. And so that's what our sun uses. Uh, burns helium. I'm sorry, burns hydrogen to form helium, and eventually our sun will start to burn helium to form carbon, and that'll be in about 5 billion years. Or so we believe, and then the sun will swell and become a red giant, and maybe consume the Earth. We're not sure about that. There's different people say different things, but there's also just like chemical reactions. There's nuclear catalysts. Our sun can undergo a nuclear catalyst called the carbon-12 cycle. So carbon-12 can react, can undergo nuclear fusion, and then go up to oxygen 16, and then that can alpha decay down to form carbon-12 again. So it's interesting that you even have nuclear catalysis in this. But then the binding energy is here. So the binding energies, the well, these elements down here, the protons and neutrons, are more massive than up here. So as the protons and neutrons lose mass, they become lighter, and they also emit energy by this equation you may have seen before, equals mc squared. So energy is mass times the speed of light squared. And of course, I mentioned the iron. So the lightest protons and neutrons are in iron 56. And iron 56 is particularly important because this is what causes what are known as type 2a supernova. Because after a certain time in a star's life cycle, enough iron will form in the core of the star. And when the iron starts to fuse, you can see it's endothermic. So gases, so stars are also gas. When a gas cools, it contracts. So when you have nuclear fusion that causes contraction, that means more nuclear fusion takes place. And if you're forming iron, then that's going to start to become, when iron starts to fuse, that's endothermic, which causes the star to contract, which causes more nuclear fusion, and so on. And that causes an issue where the star's core collapses. And as it's collapsing in itself, it causes a shock wave to go out the star, and then that causes what's known as a supernova, and then the star gets really bright and burns a bunch of fuel and generates various heavier elements. So you can form heavier elements various different ways. That's one of them, is from supernovas and stars. Another one is you can have neutron stars collide. So if a star is 3 or more solar masses, it can form a neutron star. So the neutron star, there's one called a pulsar, which is basically it's neutron. It's just a bunch of neutrons held together, and they spin very quickly. And then if it's very massive, it can form a black hole. But well, that's for a different class. So, but the point here is that we have, depending on the nucleus that we're in, we have nuclear binding, we have various binding energies, and that's the consequence of that is with nuclear reactions, whether or not energy can be evolved from that. So let's look at this. And the amount of matter that's lost is called the mass defect. So, and again, this one I didn't write out because it can be explained better just by using this. Calculate the mass defect in nuclear binary energy per nucleon for carbon 16, and has a mass of 16.014701 atomic mass units. So the mass defect, you have to figure out what the resting mass, the unbound mass of 6 protons and 10 neutrons are. So the number of neutrons, it's 16 minus 6 or 10. And those are the resting masses of a proton and a neutron. It's 1.00783 atomic mass units and 1.00866 atomic mass units. And notice that a neutron is slightly more massive than a proton, because a neutron, among other things, is kind of like a proton plus an electron. So you sum that up, and then you subtract the original mass of the carbon 16, and you get 0.118879 atomic mass units. And then there's a conversion. This is one atomic mass unit. That's found by E equals mc squared. And each atomic mass unit is 931.5 mega electron volts. An electron volt, so mega is 10 to the whatever, 10 to, it's a million, 10 to the 6. Electron volt, if you're wondering, electron volt is equal to 1.6 times 10 to the minus 19 joules. So if you want to know what this is in joules, you can multiply that way. You can, the mega electron volt. And an electron has a mass of about 0.51 mega electron volts, for instance. And okay, so let's see here. I say I did it again. I use mass energy interchangeably. So then this is the binding energy, because you multiply. You have the mass defect in atomic mass units and convert it to mega electron volts. And then there is 16 nucleons. So we're losing about 7 mega electron volts of energy per nucleon. So that's the binding energy, or how much is given off by this when this forms, hypothetically. Okay, so I mentioned fusion is better. So stars undergo nuclear fusion. Also nuclear weapons, so the hydrogen bombs, those can undergo nuclear fusion. So some bombs are just fission bombs. You can have bombs that have nuclear fusion as well. So that's a proven form of nuclear fusion that we have. There's the tokamak fusion reactor. The textbook talks about this. It's a Russian design. You basically have a big kind of a donut. It would, if anything, if you've seen the movie Iron Man, that's kind of looks like whatever I forget what they called that thing. It's kind of like that, the reactor that they have in Iron Man. But of course, it's bigger for the tokamak. They excite plasma and they swirl it around, and as it's swirling around, they collide, and that causes nuclear fusion. And the people that run tokamaks, I mean, the idea with this is they're trying to get a nuclear reactor that'll be self-sustaining and can generate energy this way. But the tokamak operators, they say, when are we going to have nuclear fusion? They're like, oh, we'll have it in 20 years. And they're like, well, what happened in the past 20 years? Like, oh, we figured it'd be 20 years there ago. We're not anywhere close figuring out how to make nuclear fusion happen in one of these. And one of the operators told me, he's like, well, what's wrong? He says, well, imagine you're trying to weave a basket that'll hold water out of Twizzlers. And that's kind of like the difficulty that we have here, trying to get the thing stable. So that was what he said. We have another type of fusion reactor. It's not listed in the textbook. It's the Nuclear Ignition Facility. It's in Livermore National Laboratory. What we're really doing is we're doing research on nuclear weapons, because since 1990, or I forget when we signed the treaty, we're not going to blow up nuclear weapons anymore. But we're still doing nuclear weapons research. And we're doing it using high-powered lasers. The Nuclear Ignition Facility, you can look it up online if you want. Basically, they have some really high-energy lasers shine on this pellet, and the pellet vaporizes the surface, which causes the pellet to contract very suddenly, and then that contraction causes nuclear fusion. So it's kind of like, but it fires. It's kind of like trying to heat a room using a shotgun, like pumping a shotgun and then firing it that way. It's not like a constant stream of energy. It's more like I said, like a shotgun kind of as far as its output. So, but you can read about that. Other things. So there's uh, particle accelerators. So the book talks a little bit about particle accelerators. The top here, this is a linear accelerator. So this is a linear accelerator, and basically you have a source, a proton source, and then by taking some plates, you excite the proton, and it speeds along a linear fashion, and it gets really fast. At a certain point, it gets what's called relativistic. It doesn't really get any faster in terms of its speed. It basically becomes close to the speed of light, and then if you put more energy into it, you can. The momentum of it just increases, or the apparent momentum increases. They say it becomes more massive, the argument is momentum the same thing as mass? But the momentum of the particle gets really high. This is also how instead of a proton, if you made electrons this way, that's how a cathode ray works. So we don't have them anymore unless they're really old. But a cathode ray TV, this is the same idea as a linear accelerator to form a cathode ray in a television set. On the bottom there, that's a cyclotron. So a cyclotron uses, instead of using a linear accelerator, it alternates current, and it excites things in a circular fashion, and the alternating current then will excite it up into in a swirly pattern. And Ernest Orlando Lawrence is the one who figured this out, and he got a Nobel Prize for it. And you can, any charged particle though you can put in here. You don't have to use a proton. You can use any nucleus. You can use electrons as well. So electrons, you can have particle accelerators. Something called a synchrotron that uses electrons that are really high energy electrons. And the thing with electrons, electrons are weird when they get really close to the speed of light. I mean, with the uncertainty principle, well, an electron kind of around an atom. You've seen, if you've seen the wave function orbitals, they can be spherical, kind of with the s orbitals, or like kind of like a dumbbell in the p orbital. When they're free, in my mind, they look kind of like a football. They have like a direction, and they're kind of going somewhere. When you have them in an accelerator and they're moving very fast, they get really kind of thin and pancake-like, and they really tolerate each other's presence. So electrons repel, but if you have them moving at relativistic speeds, you can really stack them up on top of each other. I mean, you can't stack them up on top of each other because that would violate the Pauli exclusion principle, but you can get them very close. You can have a lot of current in a really small space for relativistic electrons, and then the radiation coming from those can be really quite powerful with those particle accelerators. So you do not want to be in the particle accelerator when it's going on. Okay, but let's say you do. Well, this is what happens when you get hit by radiation. So, well, first of all, where do you get your radiation? You notice that we get quite a bit from various sources, the natural sources of radiation. So airplane rides, so you don't have as much of the atmosphere. So if you're up at 39,000 feet, you have a dosage of half a millirem per hour. Okay, so what is a millirem? So, well, I don't want to go through all the different types of radiation. The so what is you're allowed to get 5 rem, and you don't really notice anything till you get to about 20 rem, and then your white blood cell count can go down. It depends on the person. Around 50 or 60 rem, that's usually when people lose their hair. They can lose it maybe at 100 rem. It just depends on the person. And at 100 rem, you get radiation sickness. Radiation sickness, it affects the hair, it affects the stomach, and it affects the eyes. Is the primary thing that a lot of people get cataracts from radiation sickness, and your stomach, like the similar to chemotherapy, the symptoms are similar to chemotherapy. your hair follicles and your stomach lining are really affected, and those are the ones you feel it quite a bit. And after about 500 rem, you can die. There's some ways to mitigate that. If you have a bone marrow transplant, that usually helps, for instance. And if you go higher, you can get it can affect your central nervous system, and you just kind of turns your nervous system into something that's non-functional, and death occurs that way. That happened to some of the workers in Chernobyl, and for instance. Okay, but let's go back to, so that's a REM. So you can have 5 REM, and notice that we're at millirem. So a thousandth of a REM. And cosmic radiation, this just happens to everybody. Terrestrial radiation, that's just here, of course, on Earth. That's just from things that are on the rocks and whatnot. And we have like carbon 14, and we also have potassium 90. Wait, no, I'm sorry, potassium 40. Sorry. Um, yeah, potassium 40. That's slightly radioactive as well. So there's various things, and they we have things in our body that are radioactive, so we have a little bit of that. And radon. What's nice about here in Hawaii is that we don't really have any radon gas. Because we don't have any uranium in the soil, so our terrestrial radiation, the radon gas level, would be very low. I remember I wrote an article in the Star Advertiser after the Fukushima events, and I put my email address on there, and I got fan mail. What I mean by fan mail, I mean hate mail. People wrote me lots of hate mail. But I got a few questions, and one guy, and it was a lot of people, wasn't in Hawaii. I got one guy that was in Chicago saying, "Hey, I'm tracking the radiation in Hawaii, and your radiation level is lower than it is in Chicago, and you're closer to Fukushima. Like, why is your radiation level lower than mine? And should I be concerned?" And I was like, well, the reason why your radiation level is lower is because we don't have any uranium or thorium in our soil, and you do. And we also don't have any radon, so that's the reason why it's lower, and don't worry about it. So, okay, what other things? So, chest x rays, 8 millirem. So, you can get lots of chest x rays. You get lots of dental x rays, right? So, those are fairly high, but I mean, still millirem. Mammogram, you can see that. And I had the CT scan. There's a variant enema. Yeah, that's what I've had that before. The 400 millirem from a CT scan. And if you have a heart scan, okay, various ones there. So those are all medical procedures. Consumer products, so building materials, these have, uh, it depends, of course, where you get the building materials, but so granite's going to have a little bit more. So granite has a little bit of radon in it, for instance. Also, so if you have a watch, these are old watches. They glow in the dark. The thorium, not the thorium, the radium girls. If you want to look up something, look up the radium girls, and they were one of the ones that would paint the watches, and they all got radiation sickness from this. So you do not want to have one of these, and you do not want to wear them every day. Another one, smokers. So smokers get 16 rem. So that's getting close to your noticeable amount, and that's a pretty hefty radiation dose there to your lungs. So one thing to be careful if you're smoking a pack of cigarettes a day. So, but anyways, so what are good things about radiation? So I've had this done before. I've had a technetium 99, so I had a bone scan, and the picture down here on the right, this is of a bone scan. So technetium 99 metastable. You take molybdenum, and it'll decay down to technetium 99, and then the technetium 99 will emit gamma rays for about 6 hours, and it's just an excited nucleus. The technetium itself is unstable, but that beta decays. That's got a much longer half-life. And you can use that it's typically done for bones. Iodine 131, this has a half-life of 8 days. This is one of the ways you can find out if there is a nuclear event, is there's higher than normal levels of iodine 131. And this hits your thyroid. So also if there's a nuclear event, like a nuclear weapon, they typically will release people to take potassium iodide. And the idea with this is that it'll saturate your thyroid with iodine, and then you won't get a certain type of radiation sickness. You can still get radiation sickness, it just you won't get the one that affects your thyroid. Other things, so iron can be looked at your blood, and thallium for the heart, and fluorine 18. This is for PET scans. So the positron emission, I mentioned the positrons. So you can do this there. Here's an example of a PET scan image. It shows where there's higher activity in the brain, and they can use this to diagnose various conditions. And then phosphorus 32 for looking at tumors and various things. So I don't know how to read this. This is the bone scan. I don't know how to read either of these. I can't tell you. One thing I can tell you is that the bladder, you can see the bladder is very shiny, and that's because I remember, especially when I had my bone scan, I noticed that my bladder was very very shiny as well. And the technician said, "Oh, it's just because your body is removing the technetium." So other good things, you can use it for radiotherapy. And this is a way you can destroy something without putting someone on the knife. Let's say you've got a tumor, it's in a hard to reach place, like in your brain, and you don't want to go and do brain surgery. Well, you can shoot a beam of something like cobalt 60, and they're looking at doing other beams of things like carbon 12 or something like that. It's just you send a beam of particles, and it can go through to a certain area and then just wreak havoc in that area. And then that's a way you can cause destruction to an area without using surgical implements. And so if you know the depth of a tumor, you can just shine it with radiation and just destroy it that way, and then hopefully your body's immune system takes over and gets rid of the rest. Another way is to irradiate food. So if you want to preserve food, you can irradiate with radiation. And so the gamma rays here can do that. So if you shine strawberries at gamma rays, for instance, you kill a lot of the bacteria, like the mold and bacteria and whatnot, and it helps preserve food that way. And food that's irradiated is not going to cause any damage, so it's not it's totally safe to eat. It's not going to be radioactive at all. It's just killed the other bacteria. I mean, of course, sometimes you do want to consume bacteria, right? For like kimchi or yogurt or something like that. Then you want it to be live, or honey. Like you want there to be the live cultures in that. But so you wouldn't want to radiate that. But for strawberries, you're not picking up anything from it. So it's a way to store food and make it safe for a long period of time. Things like cereal grain products, especially if you don't want to plant them. I mean, you don't want to irradiate them. It's not that's going to be wrong to plant them. It's just it destroys the structures inside of them, and that's all radiation damage does. It's not like it gives you superpowers. It just it's an attack on a molecular and atomic level. It rips off electrons and it breaks chemical bonds, and that's the damage that it has. It can corrode metals as well. So satellites in space get corroded by, like if they go through the Van Allen belts and the Earth, they can get there's a specific type of corrosion that satellites can experience from the radiation in space. So it's not really like anything like special, and it's just radiation is just causes damage. And for you as a human, as a biological creature, being causing damage, then you have various effects. And like I said before, it tends to affect the eyes and the stomach and the hair more, because those are just more sensitive, because they they have to divide so frequently. But in general, though, humans are fairly resilient to radiation. We're not the best. I mean, we're not like fruit flies, or everyone says cockroaches, but fruit flies are really, really pretty resilient. But okay, but this is what the textbook covers. I know I could talk about it. I like this stuff. I could talk about it for a long time. But if you're interested, you can ask me some more questions. But I'll stop there.